Welcome back to the lectures in chemistry and the topic of atomic structure and chemical bonding. My name is Mangala Sundar and I am in the Department of Chemistry, Indian Institute of Technology, Madras. In the last lecture, we ended with a discussion on the model problem of a simple particle in a box and a perturbing potential that we want to apply our formulae of non-degenerate perturbation theory to obtain simple results. As an application of the mechanisms, as an application of the formulation, we started looking at this model. Okay? That is the box problem in which a potential H1, it's a Hamiltonian, that's introduced with a small constant C such that the potential varies as given here x times L minus x, where x is the position of the box, the particle in the box at position coordinate associated with the particle wave function. Okay. The zero order energies are known to us, the zero order eigenfunctions are known to us, and the properties of the eigenfunctions are that the eigenfunctions are orthonormal, and we want to calculate the first order perturbation correction to the energy En0 due to the perturbing term H1. And we know the formal expression for the calculation of the first order correction En1 is given by the matrix element of the wave function, matrix element of the perturbing Hamiltonian between the corresponding eigenfunctions of the zeroth order Hamiltonian. Okay. Therefore, it is a simple integral to calculate. In the integral result, this will turn out to be 2 by L, which is due to the root 2 by L squared, the integral 0 to L, and the psi n zeros are, since the Hamiltonian is only a multiplicative term here, it is sine square n pi x by L, and the constant, the H1 simply multiplies x into L minus x dx. Okay. So, this is a simple enough integral. I do not want to do that, I will leave it to you to arrive at the result. The correction is maybe one step. I will just write down 2 by L C, which is just to expand this L integral x sine squared n pi x by L dx minus integral 0 to L, it is x square sine square n pi x by L dx. Okay. You know that this is nothing but the average value of the position. This is the average value of the position operator that you have calculated this to be. You know that the answer is L by 2, including the 2 by L integral here, including that, and you know that this is the average value of the x square. Okay. So, I would leave it to you to evaluate. Now, what about the second order correction that we want to look at? due to the same H1, we know that this Hamiltonian is such that we can actually do corrections to various orders. The integral evaluation is a fairly simple integral evaluation involving trigonometric functions and algebraic, polynomials. Therefore, it should not be a major problem for you to do that. The second order correction, if you recall, psi n 2, if you recall this expression, not psi n 2, the E n 2, the energy correction to second order, the formula all of you know is, I don't know why it keeps coming, okay. The formula is sum over k not equal to this n and psi n 0 H1 psi k 0 psi k 0 H1 psi n 0, okay. The sum is for both the numerator and the denominator, namely E n 0 minus E k 0, okay. Now, let us just do as a simple matter E 1 2, that is correction to the lowest zero order energy. Okay. So, the picture that you have to have in mind is the particle in a box has these energies n1 square. So, this is 1 times that unit h bar h square by 8 m l square, okay. This is the unit of energy. The second one is quantum number n1 is equal to 2, this is 4 times that energy, the third one is 9 times the energy, the fourth one is 16 times the energy, and so on. So, the quantum number is 3, quantum number is 4. Now, this is in the absence of the perturbation. Now, with the perturbation, how do these energy levels change due to the introduction? So, whether they go up or down, we do not know. They go up, or this energy goes to some other energy values, this energy may go to some other energy. So, the idea is that the exact solution that you want to find out, you are trying to find that by way of adding corrections to first order, second order, and so on. That is the picture that you have to have. And the question that I have just now asked is, what is the correction to the lowest energy E10? It is interesting from second order formulae, it is a general result that we have to remember. Therefore, let us write the correction E1 to second order correction as sum over k not equal to 1. Since we know all the formulae, we can write the integrals 2 by L, integral 0 to L. Remember, there was a psi n 0, so this is sine pi x by L, the first wave function, times c x into L minus x, okay. Then the other one is sine k, so it is sine k pi x by L dx, and if you recall, the other integral is simply the complex conjugate of this, and since this whole thing is real, it is very easy for us to write this as square, okay. Divided by the lowest energy is h square by 8 ml square, and the next energy is k square, all levels, k is equal to 2, 3, 4, etc., and we are summing over that. So, it is 1 square minus k square, which is the difference in the energy. The form is particularly important because what you see on the numerator is an absolute square, is a square, it is never negative. This is real, otherwise we have taken the number multiplied by its complex conjugate, and look at this wave function, the complex number here and its complex conjugate. Therefore, the product is always positive, 0 or positive. If the integral is 0, it is 0, otherwise it is positive. And then what you also have is that the denominator for every term of k is negative. This term is less than 0 because k is greater than 1. Therefore, you are summing only negative terms. The numerator is positive always and the denominator is always negative. Therefore, the second order correction to the lowest energy is always negative. This is for non-degenerate states, problem that we have looked at. The result can be more general. The second order correction to the ground state energy due to perturbation theory. We are looking at specifically here of non-degenerate states. But let me not worry about that. The second order correction to the ground state energy due to perturbation theory is predicted to be negative. Okay, it's a general result. So, this correction term that you have for the second order to the ground state energy, again this integral is something that you can calculate, and you see that it involves sin pi x and sin k pi x, where k is not equal to 1, and it has the perturbing term x into L minus x, the coordinates. Therefore, this is the off diagonal matrix element of the perturbation in the eigenfunctions of the 0th order Hamiltonian sin pi x and sin k pi x. So, everything that we said earlier is illustrated here. Okay. Now, again I will leave it to you to calculate the integral. It's a very simple form. Okay. Essentially, if you recall, an integral of this nature, sin a x sin b x x raised to n 0 to L dx should be, one simple way is to write this as the it's a sin, so you can write this in the double angle formula, namely 1 by 2 cos a minus b x minus 1 by 2 cos a plus b x multiplied by x raised to n integral 0 to L dx, and then cos x raised to n can be done using partial integration. But if you find your own way of doing things, easier way of doing things, is perfectly fine. But if you are sort of lost on how we do this, this is how one normally does this. Use partial integration, namely cos ax x raised to n integral dx, for example, 0 to n 0 to L
here we have a prime, let us put in, is to be written as integral 0 to L d of sine a prime x by a prime x raised to n, and then you can use this UV formula, namely sine a prime x raised to n by a prime, that is equal to between the limits 0 and L minus integral 0 to L 1 by a prime n x raised to n minus 1 sine a prime x dx. And you can repeat this process until you get rid of the powers n minus 1 x raised to n minus 1 to until you get rid of this n minus 1 powers to 0 successively. Okay. So, that is just a algebraic step in case you wanted to know quickly how to do that. So, I will leave that point. The next simple example for perturbation, we shall look at the harmonic oscillator model. Okay. And we know the solutions of the harmonic oscillator. If you do not, please go back and look at the solutions. I will write the results, because we need the 0 order Hamiltonian, which is minus h bar square by 2m, the mass of the oscillator, d square by dx square plus half k x square, the force constant of the oscillator. And in terms of the frequency of the oscillator nu, it is 1 by 2 pi square root of k by m, or omega, which is 2 pi nu, the angular frequency is equal to k by m. Okay, you know recall these results, and the 0 order energy E n 0 is h bar omega times n plus a half, where n is the quantum number, is equal to h nu n plus a half, depending on what unit of energy frequency that you use. N goes from 0, 1 to 3, etc. And therefore, you see here the index takes 0 as the starting value. This is the lowest energy. Okay. Also one dimensional, therefore, the harmonic oscillator energies are one dimensional. The harmonic oscillator energies are non-degenerate. Okay. And the wave functions, somewhat more complicated than the particle in a box. The wave functions are given by a general formula with a normalization constant n, which is a function of, which is dependent on n, times an exponential minus a constant alpha x square by 2, I will just write down, and the Hermite polynomials of the argument root alpha x, where the constant alpha is a function of the harmonic oscillator parameters, namely the mass and the force constant, and alpha is given by k m by h bar square, the Planck's constant, divided by 2 pi 1 by 2. Okay. So, this has the dimensions of L inverse 2, and this is the harmonic oscillator eigenfunctions. These are the harmonic oscillator eigenfunctions. Okay. The general formulae, and the Hermite polynomials, expressions for the Hermite polynomials are given in all the textbooks. The lowest order, the lowest energy solution we will write down, which is psi 0 0 of x. The normalization constant turns out to be alpha by pi to 1 by 4. the Hermite polynomial when n is 0 for all argument is 1, therefore, all that you have is e to the minus alpha x square by 2. Okay. This is the lowest eigen energy eigenfunction or eigenfunction for the lowest energy state. Okay. And suppose we have a perturbation which is not a harmonic force, but maybe the second order. So, the perturbation is like a cubic term. You remember the harmonic oscillator Hamiltonian has half k x squared, the harmonic term. Higher powers x cube, x4, etc. may contribute to the oscillator if the amplitudes are larger than what is known as the harmonic or small amplitude limits. Then the energy levels change due to this unharmonicity or non-harmonicity. So, if we assume to simplest order a perturbation to act h1 of x as some constant c, okay, times x cube, okay. C obviously has the dimensions of energy divided by volume, okay, because you see x cube is length cube, so appropriate units. It is the small quantity which is responsible for the oscillator being slightly anharmonic. Okay. Then one can calculate the corrections to the harmonic oscillator energy En0 due to this perturbation H1 in a very simple way. And here there is a very nice simple result that will follow, which I will illustrate later on using a different method called the operator or the Dirac representation for the harmonic oscillators. In another lecture we would introduce that, but here we will do the integrals. The correction to, say, let us take the lowest energy E0 0, and let us do the first order correction to that. It is given by psi 0 0 H1 psi 0 0 eigenfunctions of the 0 order Hamiltonian H1, and in this case the integral is, you remember, it is alpha by pi to the 1 by 4, but we have the square. So, it is alpha by pi to 1 by 2, and the integral, the harmonic oscillator coordinates are all the way from all along the real axis minus infinity to plus infinity. I mean it is a model, and we realize that as the amplitudes are very large, the harmonic oscillator is no longer oscillator, but the wave functions are such that this limit is a theoretical limit. E to the minus alpha x square, because it is a psi square, and the H1 is the coefficient c, which is the magnitude of the unharmonicity times x cube dx. Okay. This is again by symmetry one can say immediately that this is an odd function, the integral of an odd function between symmetric limits minus infinity to plus infinity. Therefore, the answer is that this integral is 0. There is no first order correction, no first order correction. Okay. Simple result. Therefore, it is not possible for us to say that we will correct this energy. We have to calculate. The first correction to the energy is not first order, but it is second order. And again, the result for second order is somewhat simpler than what we would write down, but let us first write down the corrections, namely E, the lowest energy level 0, and the second order correction 2 is given by sum over k, the integral alpha by pi to the 1 by 2 e to the minus alpha x square by 2, sorry, alpha x square by 2, not even 1 by 2. I think we should be careful here. I will just write only the 1 by 4 corresponding to this part of the left side of the wave function, which is the ground state. Then you have c x cube, and the other wave function is kth order, which is e to the minus alpha x square by 2 n k, the normalization constant, and h k of root alpha x between the limits minus infinity to plus infinity dx, this whole thing squared, okay, divided by the 0 order energy is half h nu, and any other energy state is k plus a half h nu, so we can rewrite this as minus k h nu. Okay. Now, the integral appears like k is not equal to 0, the sum. You will find out in another lecture that the way we have written, it appears that we may have to calculate all the Hermite polynomials for different values of k and calculate this integral and so on, but in a later lecture you will find out that this expression is not as hard as it looks like, that you only need to worry about k is equal to 1 and k is equal to 3, we started with 0, or the only two terms that would contribute non-zero values to the sum. Okay. It is x cube. It is x cube. We have taken the harmonic correction, the unharmonic correction to be x cube, and I am already guessing the result from some other way of studying the harmonic oscillator problem, namely using the operator method. We will find out that you have the 0 order wave function and the kth wave function, kth eigenvalue eigenvector, and you will see for x cube that only these are the two terms. In fact, I will state the result, but will verify it later, that if we are looking for second order correction En2 to the harmonic oscillator, okay, and if we do the symbolic writing using the Dirac notation k not equal to n psi n0 x cube times c square psi k 0 psi k 0 x cube psi n 0 divided by E n 0 minus E k 0, which is essentially equal to h nu into n minus k. Okay. If we have to calculate this integral for harmonic oscillator eigenfunctions, 0 order, these eigenfunctions, okay, the general result that will follow is that k is either equal to n plus 1 or minus 1 and k is equal to n plus or minus 3 are the only terms that we need to worry about. If instead of cubic we have additional corrections like the quartic and so on, this result can in principle be generalized to adding only specific terms. But anyway, that is the other simple example. The third and the last example for today's lecture again, I will leave it to you to calculate these integrals, and if you need help on this, please look into the assignment section of the website, and you can download all these things as PDF files for your own personal use. Therefore, please supplement this lecture along with with the lecture notes that is provided on the website. Okay, the third and last example is hydrogen atom. These are the three models that you are supposed to have been familiar in the study, through the study of the first level quantum course. So in the case of hydrogen atom, all of you know that the 0 order Hamiltonian is given in polar coordinates by minus h bar square by 2me. It is a long expression, 1 by r square, dou by dou r square, dou by dou r, plus 1 by r square sin theta, dou by dou theta sin theta, dou by dou theta, plus 1 by r square sin square theta, dou square by dou phi square, corresponding to the kinetic energy of the electron in a reduced mass system, where we replace the mass of the reduced particle as the mass of the electron, because the nuclear mass is very large, minus the Ze square by 4 pi epsilon naught, or the relative coordinate of the two particle system, and we know that the energy is h naught psi n zeros. We know the solution. This is an exact problem that Schrodinger first solved, and everybody else has later on followed this by other methods as well. The answer is hc, the Rydberg constant, by n square psi n 0, and we know that this n for each value of n going from 1, 2, 3, etc., the degeneracy of the state is n square, so that when n is 1 you have only one state, which we usually label as 1s orbital of the hydrogen atom, and when n is 2 we have 4 orbitals or wave functions known as the 2s and the 3 2p wave functions, and when n is 3 it is the 3s, the 3p wave functions, and the 5 3d wave functions, and so on. Therefore, this is both a non-degenerate and a degenerate system. The lowest energy of the hydrogen atom, 1s orbital, is the only non-degenerate system, non-degenerate energy level, and if we place the hydrogen atom in a small magnetic field or in a small electric field, it is possible for us to obtain the corrections to the energies, the lowest as well as higher order, but higher order energies being degenerate. We have not yet dealt with the degenerate state perturbation theory, but we can correct the lowest order correction, the correction to the lowest energy level. So, if we assume the perturbation H1 to be of a specific form, let me see which I have used in my lecture notes. We will, yeah. So, I have used the electric field, the electric dipole moment in the presence of an external field A. This is the electronic dipole moment. Of the system, and E is the external field. The external field is treated as a classical quantity, and the dipole moment is the quantum mechanical operator. And if the field direction is chosen as the z direction, please remember that in the hydrogen atom the z axis for the sphere is arbitrary, and the moment we put in a static field we can choose the direction of the field as the z axis, and therefore if we write the electric field as z times E naught, then what we have is H1 is minus mu E naught z, the z component of the electronic dipole moment, which in the form of a magnitude is given by the value mu naught times cos theta. Please remember the z coordinate in the spherical polar system is the radius, whatever is the magnitude multiplied by cos theta, and therefore you have this expression, namely minus mu naught E naught, the strength of the electric field, times cos theta, where this theta is the same as the theta that we have written down here. Therefore, if we use the wave functions, 1s wave functions and the 2s 2p wave functions in r theta phi coordinate, we have the Hamiltonian also expressed in that coordinate system. It's immediately obvious that we can calculate these integrals as simple integrals involving exponentials and polynomials. Okay. So, let us take the first order correction. Again to E10, which is minus Hc or H, and you remember that this value is minus 13.6 electron volts. Okay. So, if we place this hydrogen atom in a small magnetic field, electric field with the magnitude E naught, this energy is likely to be perturbed. Is it first order or second order? We will find out. Okay, very quickly. I won't do the integrals, but I will give you the formula so that the integrals can be evaluated by you. First order correction E11. Okay, so let us write the wave functions. The 1s wave function. Psi 1s, which is the psi 10 or theta phi, is given by let's see. Okay, I will write the general formula for this, so it's easier. It's given by R10, the Laguerre polynomial to first order, and the spherical harmonic Lm, which is y00 theta phi, and this is a constant, it's independent of theta phi. Okay. Let me see if I have the forms here. Okay, I have not written that, but anyway we can worry about it. The integral d tau is essentially r equal to 0 to infinity r square dr integral theta is equal to 0 to infinity, 0 to pi, 0 to pi sin theta d theta, and the integral d phi 0 to pi. That is the coordinate integration one has to worry about. And if we have to look at the first order correction E11, then it's psi 10 H1 psi 10, and I have written this down as R10 or NL of R square due to the two wave functions that you have here, and the Hamiltonian does not contain any R dependency, it only contains cos theta. Therefore, we can write R square dr 0 to infinity, okay, times a mu naught. Okay. Then followed by the integral 0 to pi, we have YLM y 0 0 theta phi cos theta y 0 0 theta phi. This is the angular part multiplied by sin theta d theta d phi, and since there is no phi dependence here, we can also write this as 0 to 2 pi. Okay. So, just let me make sure that the pi is associated with the theta integral, and this is the integral that one needs to evaluate. With all these elaborations, okay, you will be very disappointed to know that this integral is actually 0, okay, because of the properties associated with cos theta, sin theta, d theta, d phi. Y 0 0 is a constant, it is 1 by root 4 pi. Therefore, the essential integral, and this is a radial function r square dr from 0 to infinity, this is the radial function normalized. So, this gives you 1 if you put in the right constants. So, what is left over is the only integral 0 to pi sin theta cos theta d theta, and the integral d phi is of course 0 to 2 pi will give you 2 pi. That will go away with the normalization constants that you have already defined. This integral sin theta cos theta d theta is 0 to pi is integral 0 to pi 1 by 2 sin 2 theta. And please remember, sin 2 theta in 0 to pi actually completes one whole cycle, 0 to pi. Okay. Therefore, the area cancels out, okay, which is what this integral is. The area cancel out and this whole thing goes to 0. So, I mean, doing all these things, finally one recognizes that there is some symmetry involved, and the first order correction is 0. So, now it is possible to do second order correction by using all other hydrogen atom wave functions. I will not do that, but this whole exercise, today's lecture, is to give you an illustration of how to use the formulae that were proposed in the last two lectures. We will continue this in the next lecture with what is known as the known as the degenerate state perturbation theory, and you will find out that all we need to do is one small modification of everything that we have done in the non-degenerate perturbation theory in order to solve problems in which the states, the 0 order states, are degenerate, and the perturbation spoils the degeneracy, or I mean in a more flowery language one can say it lifts the degeneracy and makes them non-degenerate. It is possible that the perturbation lifts all of the degeneracy out, or it is possible that it only lifts partially the degeneracy and so on. That depends on the problem that we choose, but it is a slightly more interesting problem. With that, the time independent perturbation theory account will be reasonably complete for our level that we are dealing with. Okay. Until then, thank you very much.